So what I would like to first of all, I thank the organizer for having inviting me for this to a little given an excursus on what MOX has been doing this 20 years towards industrial innovation and sustainable development. And indeed, it's quite a long story, but I would like to, I have organized my talk into these three sections, let's say. First, I would like to remind, because it's not everybody is aware of the impact of mathematics in industry and economy. So, and I will give some highlight about that. And then I will take advantage of some showcases, some examples of our interaction with industry in the MOX, and try to give a common line of this experience, and then a little talk about the next challenges. So. No, everyone is aware of the strong impact of mathematics in the industry, and particularly in the economy. In 2014 and 2019, there were some studies that were financed by some mathematical association in Netherlands, in United Kingdom, in France, and in Spain, really to investigate how much mathematics impacts on the economy of a country. Here I'm reporting only some extracts of the findings of these studies that were made in Netherlands, UK by Doolittle, while instead in Spain by another local company that does this type of analysis. As you can see, I'm mainly concentrated on the column on the left, on the right, the gross value added, that is the contribution to the gross domestic product given by a certain activity. In particular here, activity related to mathematics, so activity related from people with competence, with formation in mathematics. And is divided in direct, indirect, and induced. The direct is the direct contribution of the people. The indirect takes into account also the fact that, of course, activity generates other activity, and there are two levels of indirection when you go to the induced. And you can see that the percentage is quite high. And if you look at the total, the mathematical induced activity can create up to 30 or 43%, can be responsible 43% of the gross value added of the country. Similar results, you can see them in the other table in the lower right, where we have the result of the Spanish findings, and you see that surprising, even if Spain is quite different than from UK and Netherlands, more or less the numbers are let's say similar in the case of the Spain results, more or less comparable to that of the Netherlands, while UK is a more, let's say, technological society, and you can see it also in these numbers. On the lower left part, instead, I just wanted to mention also the relation between competitiveness of a country and the knowledge of mathematics. The knowledge of mathematics as measured by the PISA, OECD's PISA score. Okay, in 2013, unfortunately, this is the year where this analysis was made. And as you can see, there is quite a reasonable statistical correlation, at least, between the two quantities. Unfortunately, Italy, I put just an arrow to indicate where Italy is not very well placed in this category. So this just to show you that the mathematics is of course science, but it's not only science. Has a very strong impact in the modern economy. And indeed, here is a picture that I wanted to show about how you can match, of course is an approximation, mathematical teams, say, or mathematical theories, against keywords of Industry 4.0. So in Industry 4.0, you know, was an effort to innovate in industry, and there was some let's say, specific goals, autonomous robots, simulation, system integration, the Internet of Things, cybersecurity, cloud computing, additive manufacturing, augmented reality, big data. And inside the circle, I have put some of the, let's say, mathematical fields that would that have contributed or they are contributing to the specific goals. Control theory, numerical analysis, of course, in the simulation, for simulation system integration, network analysis, we were just mentioning, cryptography, high performance computing, topology optimization, imaging, and statistics. So, and let's see what, in our experience, towards industry, which were the main challenges for the numerical model, the main challenge we were called to face. I put a little bit the main keyword, the main, let's say, aspects. First of all, multiphysics. Nowadays, in the industry, it is very important to integrate tools that were maybe in the past developed to solve a single aspects. Structural analysis, fluid dynamics, thermal analysis, or whatever. Now the focus is always on integration, on having, so tackling multiphysics phenomena. Optimization is another very big keyword that we have met in many of our projects. Parameter estimation, take into account of uncertainty, but also, and put it in the other two boxes, the blue boxes, it is very important to be able to integrate in the industrial workflow. In the relation with industry, you need to eventually to provide an answer that can be used inside the industrial workflow, and we will discuss a little bit about that. And of course, integration with data, and that is particularly also in the view of the future. A common background of what we've done in many of our projects, not all, but of all the 100 projects that I was mentioning, but in many of them, one focus was to develop fast but accurate solver. So keywords was on, let's say, generic model reduction that, however, could have been declined in different forms: geometric reduction, reduced basis, DROM, mesh adaptivity, split scheme. So having is not only important to develop accurate algorithm, you need also to find a way to perform in a time that is compatible with the industrial workflow. And so here I just do some showcases as well as Pier Cesare did before I on some of our projects. This is a work that is related to energy transition, because you see we are moving very much on alternative sources of energy. One is wind. Exploiting wind, offshore wind plants, and you need cables to transfer the energy from the turbines to the grid, and we have to face how to build those cables so that the power loss are minimized. And that was the industrial objective: find the optimal cable configuration to reduce power losses due to eddy currents and hysteresis. And indeed, one possibility is to go to 3D standard magnetostatic simulation of the cable, but that will require an incredible amount of time if you have to study different process, different scenario, or if you want to implement some optimization strategy. So the answer here was to reduce a 1D reduced model for the wire and develop a special integral formulation of the problem, and moreover, exploit some symmetries of the problem to develop very fast and parallel solvers. And here is just a picture just to show some elements of the model reduction. Of course, I'm not going absolutely into the details, but what I want to point out is in fact the picture on the right, where you can see that by this new model we were able to get reasonable results, so results with an accuracy that was sufficient for the purpose, for the industrial purposes, but with 4 orders of magnitude gain with respect to a standard finite element solution. And another aspect where model reduction in a different sense here is present is in the work that has been done in collaboration with Thales Alenia Space on topology optimization for additive manufacturing. Here is, topology optimization is to find the best allocation of material inside a design domain to optimize a quantity of interest, for instance, the resistance of the object for the application at hand, and is getting a big the interest in topology optimization is increasing a lot because of the possibility given by 3D printing. Now 3D printing allows to print shapes that before were not possible to generate, and so the importance of topology optimization is growing. However, also topology optimization is a lengthy process, and here the study concentrated on using mesh adaptivity, in particular a particular type of mesh adaptivity, an isotropic mesh adaptivity, to improve the topology optimization process, reducing at the same time the computational cost. And here you can see on the picture on the top an object and the grid that was used to describe the object, and you can really notice how the grid had been adapted just to be able to capture the shape of the object with sufficient accuracy without, however, using extra elements, so reducing the overall computational cost. And there will be a talk by Simona Perotto this afternoon that she will give more details on this adaptation technique that is now being implemented in a spin-off that she's leading. Topology optimization can also be done at the micro scale, so not at the for designing the final piece, the final object, but to find the best microstructure to guarantee certain characteristics, certain mechanical characteristics. And also here, the mesh optimization can help. We worked a lot in collaboration with Eni, the Italian oil company, for math for energy, for the exploitation of energy resources. And indeed also here, if we want to have a sustainable economy, not only we need to try to find new energies, but also to better exploit also the traditional type of energy resources. And one important issue is to take into account of fractures. Subsoil is fractured. Fractures can appear at very different length scales, can be faults, very big scale, up to very small fractures, and they are ubiquitous. And if you want to exploit correctly the subsoil, you need to take into account the fractures. And this is true for not only for hydrocarbon extraction, but also for geothermal transportation or for the CO2 storage facilities. Taking into account of fracture is not so easy, because the biggest fracture at least must be explicitly represented inside your domain. And here the company wanted really an answer that could be used directly in their workflow, okay? And so the idea was to try to develop some embedded methods that did not require the company to change the code, but that could be integrated directly in their simulation tool, but giving the effect of the presence of the fracture. And this has been done by developing an offline type of activity that consists in analyzing the network, computing all the intersection, all the properties of the material, and so on. But the result is to create what they're called transmissibility, that in fact are then implemented inside the black box solver of the company. So modifying the parameter inside the solver so to take into account of the presence of the fracture, and you can see how this indeed has been obtained in the picture where we show some simulation. This is the final showcase, is model reduction for packaging industry in collaboration with Tetra Pak and MOX, and you will have a presentation soon by MOX CEO. And here again, here is a complex fluid structure interaction problem for making the package that contains the liquid material, milk or whatever. And again, here the answer was to develop both models, reduced models, physics reduced models, like you see here. So treating the different components with 1D or 0D models, but also more recently for the more complex parts where you really need to have a description of the flow field, a more detailed description of the flow field, to use reduced order modeling that consists in trying to represent the manifold of solution with respect to the problem parameters, and when you have obtained this map with an offline activity, then you have a very fast solver to represent also complex phenomena like fluid inside that type of geometry. What are the next challenge? The next challenge is my opinion, is integrating data in physics-based simulations. And indeed, this is just a reduction, let's say, of the general view that Alfio gave in his presentation. Here, just focusing only on some aspects. On the left, you have the data, let's say, the data world, and on the left you have the physics data world, and on the right the data analysis world, where you and the two realities can interact in many ways. For instance, we have seen that computer simulation can provide synthetic data to complement the data available for a statistical model or a deep learning model, but at the same time the deep learning model can provide constitutive laws or can be used as an upscaling technique for to be integrated in your mathematical model. Then surely we will see in some people who are talking about physical informed neural networks, where instead you do the opposite. The background knowledge given by the mathematical model can be integrated inside a deep learning type of procedure. So the integration of these two worlds, I think, will be also the key for the next activity in collaboration with industry, because industry is producing a lot of data now with sensors and they sometimes they don't really know what to do with that data, but they also have a lot of background knowledge integrated in computer codes, and the important thing is to try to take advantage of the existing knowledge and exploit the new possibilities given by the big data revolution. So this is just to draw the conclusion that I've already told. Mathematical tools and computational techniques may improve industrial project and production, provided they can be integrated in the industrial workflow, and that requires often a lot of ingenuity and a lot of particular and really selection of the appropriate technique, the appropriate algorithm. The integration of physics-based and data-driven models is an important challenge for the future. And finally, I want to mention that all that requires an interdisciplinary attitude that could be found in MOX. And this is also, let's say, a prerequisite for all the activity we have done in the past and the one that we are going to do in the next 20 years. Thank you.
Thank you very